contact me about anything. If you don't get the chance, you should have a lot of time to talk to each other, hopefully. So the purpose of this is, it's a little unclear at what level you are interested in convection. But I understand you're all interested in convection in models. Okay, so we will mostly talk about convection in models. So that's the purpose of the next 3 days of lectures, and then we'll also, hopefully, we'll organize some interactive discussion sessions, probably on Thursday morning, because there's time, I have time on Thursday morning. Okay, so since I wasn't quite sure what everybody knows about convection, it's actually quite difficult to design a bunch of lectures to a large group like this, all with very different backgrounds. So what we're going to do is today, we're going to talk about, and there's 2 lectures today, 2 tomorrow, and 2 on Wednesday. Okay? So today we're going to talk about what convection is. You may all think you know what convection is, but I'll ask you a question in about a minute, and then we'll see. So we all think we know what we mean when we say convection. So we'll talk about what is convection and what does it do. Why do we care thinking about convection? And even if you know everything I'm going to tell you, you're probably going to get my take on this. You've had all your professors at universities tell you about convection. They all have different perspectives, so I have my own perspective. The first lecture will be reasonably theoretical, just to get us all on the same page when we start using terms and throwing words around. The second one today is more about sort of what convection does to the atmosphere, why it might be important, and what the challenges might be. Tomorrow, we'll spend the entire day talking about how do we represent convection in climate models. So it's mostly about models where the resolution of the model isn't small enough for convection to be actually calculated by the model equations. And instead, we need to use something called parametrization, right, to represent convection. You've all heard the term. And tomorrow will be largely about, how does that whole parametrization thing work in principle? What are the basic ideas? Okay. And then on Wednesday, I was going to give 2 lectures, and that's the most flexible part. So if you feel we want to do something else, you tell me and we do something else. But on Wednesday, I was going to talk about recent research we did. 1 lecture on research and observations to learn new things about convection, but all with the idea on how do we need to represent it in models. And the second one would be a lecture on a new approach that we're trying to take to represent convection in climate models. Okay? But we don't have to do those 2, because I also have a lecture to the Meteorological Society on Thursday, and a lot of that will be in there. A lot of the material, condensed obviously, would be in those lectures. Okay, does that sound like a good plan to you? Are you happy with that plan? You happy with that plan? You don't look convinced yet. I need to warm you up. All right, you're not relaxed enough yet, so you need to relax. Because if you're not relaxed, it's not going to be fun. I mean, this is meant to be fun. Okay. All right, I'm going to use this fancy pointer here. Look. Very, very fancy pointer software. The nice thing is that if the lectures are recorded, then the pointer is recorded as well, and rather than a laser pointer, which you can't see, basically. Right? Fancy software pointer. Okay. All right. So let's get started. When we think convection, here are the sorts of things different people will talk about, and they're all related to convection. So this is, in our atmosphere, what are the bits and pieces that we associate with convection? And we start from the sort of shallowest and smallest bits. So one of the things you probably don't think about necessarily is stratocumulus clouds are convection. They're part of the top of a convective boundary layer, well-mixed convective boundary layer, and convection is going on. And then we have shallow cumulus clouds and the trade winds, and that's convection, right? So when people say convection, the one that most people talk about is, of course, thunderstorm type convection. So those are individual cumulonimbus clouds or multicellular thunderstorms and so on and so forth. And we all call that convection as well, right? Yeah, I don't think there's anything controversial I'm saying here. There's a term that has become very popular and often misused. There's sort of organized convection is something we use, and we'll talk about that a little bit as we go along. And what we usually mean with that is sort of squall lines and big bigger mesoscale convective systems, which are made out of many, many thunderstorms in a line, when it's a squall line, or in a big blob, like in the MJO. Hurricanes are associated with convection, so tropical cyclones, I understand you had one last week in India, so obviously there's a lot of convection going on in tropical cyclones. And then we even go to larger and larger scales, and we have whole features on the planet that we can see when we make averages, like the ITCZ, the monsoon, the Walker circulation, and we draw little convective clouds. When we draw for students, right, we draw the diagrams on how they work, there's always a little bubbly convective cloud. So that's convection. Two, we care about convection because for two reasons. One is it affects the budgets of heat, moisture, and momentum of the atmosphere, because it moves that stuff around. And it makes clouds, and the clouds themselves then affect the radiation budget of the atmosphere. Right? So we care about, and finally, rain comes from clouds, so convection makes a lot of rain. Because it's often very intense, it can make a lot of rain in a short period of time, so we're interested in it from a weather perspective, because it's changing, it's potentially dangerous flash floods and so on and so forth. All right, so that's all convection, okay? Fine. Do we all agree with that? Here's a few pictures of convection. Again, some of them are related to what we just talked about. Here's a picture of a hurricane hitting the US. Here's a shallow cumulus cloud. Here's a really strong supercell with a tornado coming out the bottom. But then there's convection here, which is sort of not in the atmosphere, but that's also convection. And that's the very famous Bénard type convection in a fluid. And these are just plumes of smoke. So, my first question to you is, all this we call convection, but what is convection? What is the definition of convection? You ever thought about this?
Transfer of heat from one system to other.
Yeah, but there's a, yes, that's what convection does. It's not how it's defined. What is it, when we, all these things we call convection, from thunderstorm to shallow cumulus to plumes, you know, to stuff that goes on in hurricanes, but what's the uniting thing? Uniting thing is the force that makes convection. What's the force that makes convection? Buoyancy. So the key thing is, everything that we call convection is something that's driven by the buoyancy force. All right? So that's, if you didn't know that, it's sort of not terribly surprising, but it's worth taking a step back every now and then and think about. When we say convective motion in the atmosphere, it's motion where the primary force, it's not the only force, but the primary force for that motion is the buoyancy force. All right, who knows what the buoyancy force is off the top of their head? See, I didn't think so. So we're going to look at what it is. So I have it on a slide here, but I'm also happy to derive it for you on this board. And I will do a few mathematics derivations, especially in the first lecture, but also tomorrow. The purpose of those is not to do the mathematics perfectly in blah, blah, blah. The purpose is to remind most of you and also to provide you with material that you can't find in textbooks. Tomorrow in particular, we're going to derive something called the mass flux approximation. And it can be a bit tedious and will take 5 minutes, 10 minutes to work through. But the point is not for you to learn the mathematics, but to actually learn the concepts that are behind. And it's usually not written down in textbooks, how it's done. Right? You remember textbooks? So the textbooks would go, okay, we start with the vertical momentum equation, we do something, and as one can easily see, this is the result. And I usually can't easily see it. I don't know about you, but they say as is easily seen, and you go like, okay, I can't. Easily? What do you mean easily? All right, and so instead of telling you as is easily seen, I'll at least give you a flavor of the derivations that are involved, okay? So we do the first thing. This is the mathematics of buoyancy. So let's do the mathematics first, and then we think about physics, okay? Because that's how textbooks work, and I hate it, because mathematics doesn't really tell you much about physics. But let's do the mathematics. So we start, I need my glasses, otherwise I can't do anything. Don't need this. So we start with the vertical momentum equation, right? So this I won't derive, but that basically, I've already written it down, and I told everybody who can't see it from the back, bring your binoculars for the next lecture. All right, so you can see it. So this is the acceleration in the vertical, right? It's a change of vertical velocity in time, and that has only two terms in the atmosphere. One is a vertical pressure gradient that sets up to balance gravity. I don't know how much you've thought about that. That's actually quite cool. Why is there vertical pressure gradient? And the gravitational force. And if the two are in balance, we call that hydrostatic equilibrium, right? And that means there's no acceleration in the vertical space. We'll come back to that. And then the next thing we always do, and this is, we divide our variables up. So say the pressure, we write it as a, this is my thingy. We write it as a mean and some perturbation from that mean. This, we can introduce this now because we're going to use it quite a bit. In modeling, climate modeling, that mean is usually a mean in space. And then the prime is a derivation. So at every point, if you think of this as space, at every point in the grid box, the pressure would be some average over the grid box plus some perturbation, some anomaly, if you wish. If you work in climate, this is also often called the anomaly. All right? So here we have two variables. G doesn't have such a thing, that's constant everywhere. So we have two variables to consider where we want to do this, if we want to work out how the vertical velocity change. One is the pressure, and the other one is the density, right? So we write both as this. And then we make a very important assumption, and that is that the mean atmosphere is in hydrostatic equilibrium. So dP bar by dz is minus rho bar times g. Yeah? Remember this from your university days? Very simple. Okay, so then we need to put this into our equations. So then dW by dt simply becomes minus 1 over rho bar plus rho prime. Easy enough. D of P bar plus P prime by dz minus G. Okay, and now comes the not so easily seen part. Alright, so this part's kind of simple, you can split this up. G is simple, you can split this up. This term is kind of nasty, right? What are we going to do with that one? So what we want is an expression for this term here. 1 over rho bar plus rho prime equals what is the question. The first trick you need to know, we take a 1 over rho bar out of this thing, and then it becomes 1 over 1 plus rho prime over rho bar. Alright? Yeah? So far so good, no approximations. Now you need to do your mathematics. This is the not so easily seen part. Alright, what is this? And what this is, we know for a geometric series, if this thing is small, then we can write the sum of n equals 1 to infinity of something a r to the n minus 1. I'm making these symbols up as we go along. Is this a over 1 minus r. Now if we look at our term here, for us, this means a is 1, right? Because this is the a here at the top, and the r in this expression is minus rho prime over rho bar. Okay, now we do typical lecture stuff in that we take the top off and go from there. Okay? Does that make sense? So if you look at this, you compare to this, then a becomes 1. So that means we can write this as this series. Okay? So that's nice. So 1 over, what are we trying to calculate? We're calculating this term here. And this is now 1 over rho bar. But instead of using this, we now expand this into this geometric series. So the first one is n equals 1, so r to the power of 0 is 1, a equals 1, so we get a 1. Okay, the second one, n equals 2, we get 1, and then we get minus rho prime over rho bar. And the next one, surprise, surprise, plus rho prime over rho bar squared, and then I won't even bother writing the other ones. Okay, and then we make a very simple assumption. We always make, and that we keep that in mind, we'll make it a lot as we go through these lectures. That's the product of two primes is so small that we can neglect it. So we just throw it away. So then really our 1 over rho plus rho prime is 1 over rho bar times 1 minus rho prime over rho bar. Approximately. I should make this an approximate. Okay, so that's the only hard bit. Now we need to plug that back into this equation there. So I'll keep it there. Ah, that's very cleverly done. You can't see anything anyway if you're at the back, right? So you have to bear with me. As I said, we won't do too many of those, but we'll do a few. Okay, so plug that in. So dw by dt equals, this term is now minus 1 over rho bar times dp. So we've split this up into two. So that's the first one by dz, p over p prime. And then the second one is a plus 1 over rho bar, because minus minus gives a plus. Rho prime rho bar times dp bar plus p prime dz. And then we have a minus g that we mustn't forget. Okay, now we take those apart. Alright. We're almost done. Bear with me. So there's this term, minus 1 over rho bar dp bar dz. There's a minus 1 over rho bar dp prime dz. And there is a plus, you get this right, 1 over rho bar, rho prime, rho bar, dp bar dz. And then there is a plus 1 over rho bar, rho prime, over rho bar, dp prime dz. And there's a g, minus g. So, okay, but luckily this will become much simpler. Oh, I wiped it off. This one was g, remember, because the mean atmosphere was assumed to be in hydrostatic equilibrium. This one we can do nothing about, so I'll leave it. This one has a product, oh no, this one again has a 1 over rho bar. This becomes a minus g, rho prime over rho bar. This one has the product of two primes, so we can neglect it, and then we have minus g. The plus g goes with the minus g, and we end up with the equation that's on the board. Okay, so done. Job done. Congratulations, everyone. We've derived buoyancy. All right. Now what? When you then read the textbook, the next thing they tell you is, from this equation, we can see that convection. So there's two terms that accelerate parcels in the atmosphere. The first one is this pressure gradient term related to the pressure difference from the mean. Okay, so if the pressure is homogeneous, this doesn't exist because we're in hydrostatic equilibrium. But then there's this other term here, which is the buoyancy. It's called the buoyancy acceleration. And it accelerates parcel under the influence of gravity. That's what you read in the textbooks, right? It's the acceleration of parcels under the influence of gravity. The first thing that immediately you should say is, excuse me, I don't get this. Because in convection, parcels go up, right? However, gravity pulls stuff down. So how on earth can, due to gravity, how can things go up due to gravity? It doesn't make any sense, right? But it is what the textbooks say. So, not a good way of thinking about this. So, to understand this, we better look at the physics, okay? So we do some physics now. No math on the board. So the way it's explained, this is from Kerry Manuel's textbook on convection. The way this is explained is usually like this. you take a fluid which has a certain density, ρ2, and in it sits a body, in this case a lovely cube, which has a density ρ1. Okay? And then you need to start thinking about the forces that act on this cube to understand why it might go up in the atmosphere. Right? So, or in this system. So the first assumption that is usually being made is that the fluid in which this body is suspended is in hydrostatic equilibrium, which means we can write the pressure change with height in this fluid as just minus the density times gravitational constant, right? So easy. So because this density we also assume the density is constant in this fluid, then we can work out what the pressure is at every level in the fluid. It's just the density times GH. Okay, very simple. Okay, now we can start looking at forces. And for convenience, we make upward forces positive and downward forces negative. So the first thing is, what's the force on this body at the top? We're only interested in the top and the bottom, really. So at the top, it's the density of the fluid times G times the height into the fluid, and we call it H1, times the area on which this force acts, delta X, delta Y. Okay? So that's the pressure times the area. That makes the force. You may remember that from physics. So the first bit's the pressure, calculated using this. The second bit's the area of the cube. Very simple. So at the bottom, same thing, except that it's the second height here, right? This height, delta X, delta Y. And then there's a third force, and now that's the one force we all know about, that's gravity. And so the gravity bit is simply the mass of this cube, and that's just its density times its volume. And then you have to get the force, it's mass times acceleration. The acceleration is g. All right, so that's gravity. So now we want to know what is the net force on this body. And to do that, we need to add those three forces up. So we do that, right here. So this is just H2 minus H1, that's this bit here. And this is the gravity bit. And what we can see is that H2 minus H1 is, of course, delta Z. It's just the height of the cube. And so the force, the net force that we get is this. It's G times the density difference times the volume of the cube. Excellent. So if we want to know what the acceleration is, which is what we calculated over there in a simple mathematics example, we need to divide by the mass of the body, which is ρ1 delta x, right? And lo and behold, we end up with an equation that looks very similar. So this is our density perturbation, and this is the density. The interesting thing, but I won't dwell on it here, is it's actually a dividing by the density of the body, not the density of the fluid. But it doesn't matter because the two are very close anyway. Then density difference tend to be small, so what you divide by is not essential. Right, so that's the physical explanation, and that looked pretty good, right? Okay, now something else to learn about convection is the air parcels that are moving around in the atmosphere that make convection. Are they cubes? Not really, eh? So is this a good example for what happens in the atmosphere? Maybe not. Is the density constant in the outer fluid? Nah, not really. So we are a bit in trouble with this example, but it's nice. We see this upward acceleration. So I forgot to say, so the upward acceleration is a result of an imbalance between the upward pressure gradient and the downward force of gravity. So it's not gravity that's pushing the parcels up, it's the pressure gradient that's putting, the vertical pressure gradient is what's pushing the parcels up. But in equilibrium, in hydrostatic equilibrium, the two forces, the pressure gradient that pushes up and the gravity that pulls down, are balanced. But if the density of a piece of fluid is different from the density of the environment, then the balance breaks down and you get accelerations either up or down, as we will see. But this doesn't work for the atmosphere. So a few questions for you. So let's look at this. First question for you. How come we talk about parcels in the air. This is a slight distraction, has nothing to do with convection, but we do it all the time, right? In meteorology, we say a parcel of air is moving from A to B and something happens to it. We lift a parcel of air, that's all in our heads. Have you ever thought about how come, are there parcels of air, really? Why not? Why do you think there aren't? Then our whole science would be complete nonsense, right? Because we all think about parcels of air. So I will convince you there are parcels of air, but why are there parcels of air? So what does it mean there's a parcel of air? Well, what it means is if we draw a boundary around a bunch of molecules in the air, and we move that bit around, the molecules that are within that boundary are still within that boundary afterwards, right? Is that true? That's the question you have to ask yourself for air in the atmosphere. And the answer is they are, and the reason is that there's so many molecules that the mean free path, that the mean distance that they move is very, very small before they hit another molecule. In fact, it's something like a micrometer or so. So that means if we do draw a boundary and we imagine that parcel rises, it's in fact all the molecules within it are still there, or most of them are still there after it's risen even a kilometer up in the air. The boundary is fuzzy, of course, because a few molecules will make it out and a few molecules from the outside will make it in, but the majority of molecules will be exactly the same. So we can define a parcel of air. That's actually quite important, don't you think? Because if we couldn't do that, and the reason is this mean free path, it also tells you if you go into the ionosphere somewhere where there aren't many molecules left, then this idea of a parcel is made, and they move a long distance before they meet another molecule. This whole concept of an air parcel is becoming not so good. But luckily, most of us stay in the troposphere, and it's all good. We are good. All right, so that's one thing to think about. The second thing I want you to think about is what's pressure? We're using pressure all the time, but what is pressure at the molecular level? Do you know? Have you ever thought about it? Have you ever been taught what pressure is? Probably not. I wasn't. It's just this macroscopic concept, but really behind it is lots of molecules, right? So what pressure is actually it's the momentum flux of molecules, it turns out. So you can think of it, each molecule in the air carries momentum, and the pressure we are feeling is the flux of momentum of these molecules. So the pressure on the wall is essentially the number of molecules times their mass times their velocity times the velocity. So the mv is the momentum and the other v is the flux bit, right? So we are fluxing momentum. Okay? So that's number of molecules, the mass, and the mean velocity of the molecules. So that's what makes pressure. So that helps us to understand the buoyancy concept in a gas like the atmosphere. So that's what I'm going to try and do now. So imagine this, and I can only show it in 2D. Imagine this is this bubble of this air parcel. It has an irregular boundary, and it has a certain density and a certain volume. The first thing is the force. We first want to, again, just like we did for the cube, we need to calculate the force acting on this volume. To do that, we look at the pressure that's actually perpendicular to the surface of this. That becomes this integral here. Then you use the divergence theorem, and then becomes this area becomes the volume, and the pressure normal to this becomes the gradient of the pressure. And if we have hydrostatic equilibrium, then we know that this force, which is the overall force on the bubble, and the gravity, which you can write like this, which is just this is the mass and g is the acceleration, equals 0, and that means the bits inside the integral must be 0. It must be the same, and that means the pressure gradient equals rho g, which is our typical hydrostatic. This is expressed in 3D. Normally we express it only in the vertical, right? So then hydrostatic equilibrium simply means these two forces balance. If the density of the fluid is not the same as the density of the outside, then you get an imbalance, and that's our buoyancy force. All right. Now let's get. When did we actually start? Does anybody remember?
11:30.
No, we didn't really.
11:35.
All right. We'll make something up. We'll make up when we're finished, and then we'll continue in the afternoon.
Yeah.
All right, so we understand the buoyancy force now, and we understand that what we call convection is driven by it. So now we can do a few more things, and we can say, well, density differences is not something that we easily understand. So the first thing to remember, from here on, we are making simplifications. All right, everything you know and read about convection is often already includes simplifications. What convection really cares about is the density difference. All right, it's the density difference that makes the buoyancy force. So the larger the density difference, the stronger the. So then we have to think about, well, how can we make density differences in the atmosphere? All right. So the first thing we can do is we can say for dry air, we use the ideal gas law here. This is the ideal gas law for dry air. And then the perturbation from this is simply, you think of it, you use exactly the same rules as if you do derivatives. Okay? So the first term is simply just taking the derivative of P with respect to pressure, partial derivative, everything else being constant. So that's this term. And the second term is you take the partial derivative with respect to temperature. So the perturbation of density has a term that relates to pressure and one that relates to temperature. And then you divide by to get the buoyancy force, we need to divide by the mean density, and we get this very simple expression here, that basically the buoyancy force, the density difference can be approximated or is equal to a pressure perturbation and a temperature perturbation. Okay. Now the first assumption that most of us make in dry air, and actually for convection most of the time, and we'll see it, but we need to remember that we made it. Occasionally we need to be reminded that we made it, is that the pressure perturbation divided by the pressure is much smaller than the temperature perturbation divided by the temperature. And that's kind of true most of the time, but not always. So what that means is the parcels move slowly enough that they can always adjust to the environmental pressure pretty quickly. But if the parcels move very fast and very intense thunderstorms, this term can become important, all right? But for most applications, it's neglected. And certainly when we think about convection in climate models, we don't think about pressure perturbation because we don't know how to calculate it, basically, all right? So to first order, this buoyancy is related in dry air. It's related to temperature perturbations. And if you plug that back into the equation, then we still have this pressure perturbation term, which again we neglect most of the time. But the temperature contribution is pretty simple. If the temperature perturbation is greater than 0, right? Let's do a bit of analysis of this equation. Then that's a warm parcel. The parcel is warmer than its environment. Then we see that this dW by dt is positive, right? Let's neglect this second term here. Then it's positive. And that means if the parcel is going up, because we've defined positive upwards, it gets faster. And if the parcel is going down, it gets slowed down by this buoyancy force, all right? So depends on where, this is the acceleration, so we need to know where the parcel is going in the first place. Likewise for cold parcels, and you know this, the acceleration is negative, which means if the parcel is going up, it would slow down. And if the parcel is going down, it would be accelerated by this force. So warm parcels rise, cold parcels sink. We kind of have this. And they accelerate as they sink, and the warm parcels accelerate as they rise. Okay? So that's, in a nutshell, convection right there. It turns out that we're not dealing with dry air, of course, in the atmosphere. We're dealing with moist air, and often in convection, we see convection often, not always, but we see it because it makes cloud. And that means there's been condensation, and that means it carries little droplets, big drops, and all sorts of stuff are in the parcel. So we need to think about the other contributions. So if you are a bit more precise and assume moist air, then you get this relation for the buoyancy. So there's the temperature term, which we already know. There's the pressure term, which we've neglected before. There's a term that relates to the specific humidity. And we can see that if QV is not 0, if water vapor is in the parcel, it's actually a positive contribution to buoyancy. Do you know why?
Yes, it will be lighter than the surrounding dry air.
Yes, because water vapor's density is lower than the density of dry air, basically. So it's a positive contribution. And then liquid water makes a negative contribution to buoyancy. So if there's water in the parcel, that will slow it down. It will reduce the acceleration. This is called water loading, and it's actually quite important, as we will see in a second. In general, all of these four terms are equally important, or are important, and it really depends on where we are in the atmosphere. So for instance, if you're high up in the atmosphere, this water vapor and liquid water terms will be very small, but if you're low down, then they can be quite large. In general, so I found in a textbook by Bob House that 1 Kelvin perturbation in temperature is equivalent to 5 grams per kilogram in water vapor, 3 grams per kilogram in condensate, and 3 hectopascals in pressure. That's just to give you some numbers as to what the equivalence is. All right. And that's why we can neglect this, because really the parcels often have pressure perturbations much smaller than 3 hectopascals. Okay. The next thing that is used a lot to talk about convection, and I just want to bring everybody on the same page again, is something called convective available potential energy. Who has not heard the term CAPE? Yeah, I didn't think so, right? I thought that most of you would have heard that term before. So what is it? It's an integral of a force along the path of a parcel. And in our case, when we are interested in convective clouds, which is usually what we're interested in, then the force we are interested in is the buoyancy force. And the path that we want to integrate over is from cloud base to cloud top. Okay, that's usually what we do. So this integral in our case becomes an integral over the buoyancy force times dz. Again, in dry air, this translates to something very simple. In moist air, it's a bit more complicated, and we usually use just virtual temperature instead of temperature in this equation. What it is the amount of potential energy if we lift the parcel, if we were able to lift the parcel from cloud base to its level of neutral buoyancy, what is the energy it could potentially release? Okay, so it's not an energy that it will release. So this is where climate models who use CAPE to talk about how much energy will be released are a bit dodgy, because it's just the energy that could be released if we could lift the parcel through that atmosphere, right? Not the energy that will be released. So we still have to think, will it be released or not? If it is released, then we know how much energy there is. Because it's a potential energy, it's often used to convert to kinetic energy, hence the vertical velocity is often used to estimate what the vertical velocity of a parcel, maximum vertical velocity of a parcel might be. Okay? Alright, so who doesn't know about thermodynamic diagrams? Most of you will have seen these as well, I'm assuming, because you all have degrees in atmospheric science, one way or the other. So I just wanted to illustrate CAPE in this diagram, because we'll come back to that actually. So the first level that's important is if we lift the parcel from the surface along a dry adiabat, maintaining its moisture, at some point it will get saturated, and that level is called the lifting condensation level. Very easy, we all know that. We start our parcel from there. After it's saturated, it follows a moist adiabat, which is drawn in this diagram by these red lines. So we have to go parallel to one of those red lines, and we do. And we can see that there's a little area where the parcel is actually colder than its environment. But if it gets to this next point here, it will become warmer than the environment, and that's called the level of free convection. All right. And the reason that sometimes CAPE does not get released is that this area can be quite large, right? So down here the parcel will accelerate in the turbulent boundary layer, but the acceleration may not be sufficient, and here it will decelerate until it gets to this level of free convection, okay? If it decelerates more than it has accelerated below, it won't make it, and there won't be convection, all right? So even though there's CAPE in the atmosphere, it will not be released, because there's this little area here, and that's called convective inhibition. You would have heard about this as well. The jargon is SIN, C-I-N, right? That's the jargon that everybody's using. There's CAPE and there's SIN. And then where it hits the temperature profile again, that's called the level of neutral buoyancy. That's basically, if you think of buoyancy just as virtual temperature, that's where the parcel will stop. In reality, it won't quite stop there. It depends on how much it has accelerated. Because it has inertia, the parcel goes at 10 meters per second, because this is not a wall, it's still air, it's just the temperature is now increasing with height because we are entering the stratosphere. So depending how fast the parcel is going at the point where it hits this level, it may overshoot or not. So that's about convective overshooting. But mostly when we talk about CAPE, we stop our calculation right there, where the parcel. So the red line is the parcel, the black line is the environmental temperature profile. And this area here is the CAPE. That's how these thermodynamic diagrams are usually constructed. Okay? And this area down here, I already said, is called convective inhibition. Now, it turns out that how we calculate this CAPE thing is not obvious, right? We can make several different assumptions how we calculate it. And it turns out that these assumptions matter a lot to what the value is. So, when you read about people having calculated CAPE, there isn't just one. There's several types of CAPE, and this may be new to you or not, depending on how much you've thought about it or had to think about it for your work. But it's important because most of the time it's not specified what CAPE people have calculated. So you need to ask. You need to question them and say, so how did you calculate CAPE? And this is from Carey Emanuel's textbook. So here's the first one. The most common CAPE calculation is called irreversible CAPE or pseudo-adiabatic CAPE. And the assumption we make, and this is the one that was on the previous, now I have to go from on that. This one is the pseudo-adiabatic CAPE. And the assumption is, and the reason we calculated that is because it's the easiest to calculate. Why? Because what we assume is the moment some water forms in the parcel, it falls out straight away. It's removed from the parcel. Okay, so that means, if we go further back, here, that means this water loading term, this bit here, is not present. So the buoyancy is larger than what it really is. So the pseudo-adiabatic CAPE will always be larger than what the real parcel can experience, because the real parcel will have droplets in it eventually. Okay, so click through this quickly. Another way we can calculate CAPE, and this is another extreme, is we could assume that all the water stays in the parcel all the time. It never falls out. That's called the reversible CAPE. So you get the irreversible and reversible. So irreversible means that because the water has fallen out, if you've lifted the parcel from somewhere to, say, 500 hectopascal and you go back, you won't get the same answer because the water is gone. You can't evaporate anything, and so therefore you get a different temperature profile as you go down after going up. Reversible is obviously the exact opposite. We keep all the water in the parcel, and then we lift it, and then that means if we want to go down again, we would get exactly the same answer, because we would just evaporate the water as the parcel heats from the compression. We would evaporate the water, and so the profiles going up and going down would be the same. All right. But that's also extreme. We know neither of them is correct in the atmosphere, right? Because not all the water falls out, but also not all the water stays in the parcel. So those are kind of the two extremes. But just in terms of numbers, you get extremely different numbers depending on which one you calculate. So this is using soundings in Orlando, Florida. Carey Emanuel calculated this. The x-axis is if you do the irreversible calculation, and the y-axis is if you do the reversible calculation, but you assume that the water cannot freeze, right? It will always stay as water. Whatever was formed as water stays as water. Whatever was formed as ice stays as ice. There's no freezing in the updraft. And you can see you get very different values. So for instance, for an irreversible CAPE of 1,000, you can get a reversible CAPE of not even 250. Yeah, so very, very different number, which is why you have to ask. This is important for modeling because a lot of models use what they call a CAPE closure. We'll talk about this tomorrow. But you won't know how the CAPE is calculated, right? So you have to actually check. Some model may use irreversible CAPE, some may use some other CAPE. So it's really important how exactly they calculate the CAPE in the model to know how exactly their model works. The curious thing that Kerry Manuel points out in this book is that if you add freezing to the reversible cape, then they almost fall on a straight line again. So this is a kind of an interesting coincidence, actually. How are we doing for time?
Good.
I think we'll do one more topic, but we won't. And then in the afternoon, then we've done all the math for today. All right. I want to do one more math thing. The next thing I want to discuss with you is what does convection do to the atmosphere? All right. But to be able to do that, we need to introduce a few things. We want the end result.
Can I ask you?
Yeah, go.
So why did they overlap? Like when you add phasing in, I didn't get the physics. Why should they overlap, or why should they have?
There is no a priori reason why they should, but it happens.
So
this is just from data.
Okay.
So freezing what happens is the lower part of the cloud, of course, they're very different. The capes are very different but when you get to the freezing level, because you kept all the water, there's now a very large effect for the parcel when all that water freezes once you get to the melting level. The physics is very clear. Why now the cape values happen to be exactly identical is coincidence, I think. Right? But the physics is very important also, and a lot of climate models include it or don't include it. So as you lift the parcels, if water gets to the freezing level and it freezes, that extra energy, there's energies released from the freezing, and that extra energy is very important in real convection. We may come back to that. Actually, I don't know whether I have it in there, because there is a little stable layer where precipitation melts, which is the same as the freezing level. So if you have lots of convection, lots of anvil clouds, lots of precipitation, where it gets to the freezing level, it melts, right? Makes sense. And that introduces a little stable layer in the atmosphere, which a lot of convective clouds cannot get through. But if you can get a little bit above that level, you start freezing and the convection goes again. Which is why in the atmosphere we often see sort of three typical levels where convection finishes. One is near the trade inversion, or near inversions over land and so on in high pressure. That's the typical one being trade inversion. That's what we call shallow convection. The other one is deep, which goes almost to the tropopause, not quite, but some of it does. And then there's congestus type convection, which often terminates at 5, 6, 7 kilometers in the tropics. And that's the sort of third type. And you wonder, why is there this discrete distribution, right? So there's maxima in cloud top heights at trade, melting level, and high up in the atmosphere. And it's this melting freezing effect that's causing that middle layer one. So it is quite important physically. I think the cape thing is a bit of a coincidence. That's probably, if you think about the physics more deeply, it's probably not quite a coincidence, but it's, so it turns out that if you freeze the water that you've had to carry and keep it in the parcel, you get about the same cape as if you don't have any water in the parcel at all. Right?
Christian, before you go further down, can you just go back one slide where you showed the water loading?
This one?
Yes. So physically, water loading, can we compare it like kind of rain within the cloud, right?
Well, it's
falling water droplets, right?
It can be falling. It can also be suspended.
Yeah. Now, so this actually tells, it works to reduce the potential of extracting the potential energy to kinetic energy, right?
That's correct.
Counteracts. Right?
Yes.
Now you should go to the next, that curve of Kerry. The next one.
Yeah, okay. I see where this is going.
Yeah. So now, when Kerry plots the bottom plot,
yes,
this actually includes the water loading.
Yes.
And here I find that the cape, reversible cape, is much higher than the reversible.
Yeah, the reversible is the one that this one contains the water loading. This one does not.
So that is containing more water loading, right? Because everything is inside. Is it due to that?
Here the water loading is included, and here it isn't.
So
that's why this is smaller than that. While the wire.
Okay, that is the maximum water loading, right?
Yeah, this maximum water loading you could imagine. So the physics of the water loading is twofold. One is there's of course gravitational forces acting on the droplets, so you can think of it as a bit of a drag term. But the other one is you also need to heat the droplets to get them to the same temperature as the parcel. And the specific heat of water is much higher than air. So it takes a lot of energy to heat. So that energy then comes from within the parcel, right? So the temperature will be lower and the buoyancy will be less. So it's these two effects. There's two effects. One is the drag gravity effect, and the other one is that you have water in your parcel now, which has a completely different specific heat, right?
So in NWP model, so this dilute or undilute cape will be which is the indication of that. So as you mentioned, the dilute will be the indication of the convection there. Am I right? So because it clearly shows the reversible cape in the.
To be honest with you, it's a complete mess.
Okay.
And it depends completely on the models. So most models that I know use an undilute and pseudo-adiabatic almost, I think it's pseudo-adiabatic, ascent for deciding whether convection should happen or not. Right? This is called the trigger function. We'll talk about it tomorrow. That's often done as a very simple calculation. They don't use cape necessarily, but it's still, they make an ascent. Right? They still lift the parcel. They make some assumptions how that lifting is happening. When they do their actual updraft calculations, it's usually a dilute ascent. We haven't talked about what dilute and undilute means, but we will tomorrow as well. Actually, we will today, later. I think. No, we will tomorrow. So what dilute and undilute means, but it also means the water loading is usually included in the full updraft calculation. But I have seen GCMs recently that don't include even water loading. Some then include the water loading but not freezing, which is about the worst thing you can do, right? And so I've seen all flavors in various GCMs. So I wouldn't want to predict which model. I know two models and I know what they do. The other models have no idea.
So we are still confused in the methodology models where both dilute and undilute cape will be giving a very different.
Yes, so the Madoff's model I can tell you, because I know that one. So the Madoff's model usually uses an undilute parcel ascent for the trigger, and then it does a proper cape calculation with water loading, freezing, all that stuff's included. But it also includes precipitation, so the cape will be somewhere between those two, right? Because the irreversible is no water, reversible is all water, a real updraft somewhere in the middle. So if you have microphysics and some water falls out as rain, then the water that stays in the parcel is less than all the water that was formed. So it's somewhere in the middle between those two. The point for modeling is that you need to check. What's your model actually doing? Cape closure doesn't mean the same for every model. They mean they use cape, but which cape they use depends on whatever decisions the people who wrote the convection scheme made, right? So the lesson for you using models is if you go to someone and says my model uses cape closure, the next question, if you come to me and says my model uses a cape closure, I'll say, oh, that's great. How does it calculate the cape? Which cape is it using? And that's where most people already don't know. So it's something you need to know if you really want to understand the model. I think, we have 5 minutes, right? This watch is not the same as my watch.
Believe you.
This watch has relativity effects in it. Whereas mine is just whatever Apple says the time is. Right. I'm sort of torn. On the one hand side, I'd like to get rid of the math so we don't have to worry about it in the afternoon. On the other hand, I know everybody's exhausted, it's getting warm in here. What do you want to do? Do you want to do a bit more math now or a bit more math at the start of the next lecture? What's everybody feel like?
No.
Now?
I want to finish math.
Get rid of it, right? That's what I like to hear. So the purpose of doing math, we might not have to do much math. It really depends on what you guys already know, and so I'm going to ask you what you already know. You want to get to this equation. Who has not seen this equation? Okay, you've all seen this. Who knows how it comes about? None of you. You really don't know. Well, then we have to do the math. All right, so There's several bits of math that we can do. So this is the equation where we want to estimate how convection affects the larger scales, and that's sort of important because from a parameterization point of view, we want to know what's the overall effect of convection on the large scale. So when we say large scale, we usually mean an average over our grid box. Let's assume it's a couple of 100 kilometers by a couple of 100 kilometers, just for argument's sake. And then the right-hand side is all the processes that happen on scales that are smaller than that grid box. First question, so this equation is written in dry static energy, which is a bit unusual, but I like it better than potential temperature. But it's effectively the same thing. Just it has the same properties as potential temperature, but it doesn't have powers of R, blah, blah, blah. So who does not know what dry static energy is? You all know what dry static energy is, so we don't need to do that math. So it's CPT plus GZ, and you can show that in a dry adiabatic process, it's conserved, just like potential temperature, right? So that's why we use it. Okay, so then the next question I have, and I probably have to convince you of that, is how do we do this separation of large scales and small scales, right? And no one had their hand up when I asked who knows how this equation comes about, which doesn't surprise me, but it is a bit worrying because we use it all the time and we don't know where it comes from. It's always good to know where stuff comes from, right? You even in your clothes, you check the label where stuff comes from, right? But here you don't look where stuff comes from. All right. What's the best way of doing this? I need to think. What's the fastest way of doing this so we get a decent lunch break? So the first trick that's being used is, so from the first law of thermodynamics, if we write one way to write the equation for dry static energy is just the absolute derivative equals the heating. So this is when it's adiabatic, Q is 0, and then S doesn't change. Another equation we know is the continuity equation. And that's just, I need to write it correctly, otherwise it won't work. Plus rho times lambda V, this is in 3 dimensions, equals 0. So this is the continuity equation. So what we're going to do is we're going to combine those two. So we're going to multiply this one, we multiply with rho, and this one we multiply with S, and then we add them together. Okay, we need to do this because otherwise you won't get to this. So bear with me. So that gives us rho ds by dt plus S d rho by dt plus rho times lambda V equals rho times Q. I hope I didn't do that too fast, but it's not that hard. So that gives us, by using rules of differentiation, very simple product rule, d rho S by dt plus rho times lambda V equals rho Q. Right? And then we do the usual d by dt absolute equals d by dt partial plus v times the gradient of the property that's in there. So remember this from uni, from the good old days? So basically then this becomes a partial rho s by dt plus v times gradient of rho s. Oh, I missed an S here, right? No one mentioned it. I forgot to multiply this with an S here. Shocking. So, and it would, I noticed now, plus rho s times nabla v equals rho q. You need to shout when I make mistakes. Come on. Someone needs to call me up on it. All right. Okay, good. So you can immediately see where this leads. So we end up with an equation. Write it at the top because we need it. We need it later. So we end up with an equation that reads d rho s by dt plus nabla of rho s v equals rho q. Yeah? That's the equation. So this is called the flux form of the equations. We very, very rarely see it, because almost always we use the advective form, where it's an advection term, rather than a flux term. So usually we see something like ds by dt equals v times gradient s, and so on and so forth. That's because we've subtracted we did the opposite of what we just did. We've subtracted the continuity equation. But I put it back in because I want it back in, because otherwise the derivation of what we want to do is too hard. This makes life easier. So that becomes d rho s, and I'm not going to do all the math, but it's really, I'm going to set you on your way so that it's really easy. Equals minus d of rho us dx minus d rho vs dy minus d rho ws dz, and that equals, and then the minus rho plus rho q. Yeah. Okay, so now we have the equation that we want to work with, and now we do the usual thing, and then it gets messy, which is why we're not going to do the whole thing. For every variable in here, except one, we will write it, for instance, u as u bar plus u prime. V will be v bar plus v prime. S will be s bar, oh, that's w next. W will be w bar plus w prime. S will be s bar plus s prime. And the only exception we're going to make is on density, because otherwise it gets too messy. So we will assume that rho equals rho bar. That's an assumption commonly made. It's inconsistent with some of the assumptions we made when we talked about convection, but for this derivation, that's what the assumption that people make. Okay, so the density variations are small. The wind and the dry static energy, they all have their own variations. So you can see what we have to do now, right? Now we have to plug these things in here. And then when it gets a bit messy, there's lots of terms. Okay, so we'll do it just for fun. So rho will be rho bar, so we get d rho bar. Is that what we get? Yeah. Times s bar plus s prime dt on the left-hand side. And I'm only going to do one, well, I'm not going to even do it. d rho u bar plus u prime times s bar plus s prime by dx, and then lots of other stuff that looks exactly the same. Yeah? So we're only going to do this first term, so that, well, on the left-hand side we get two. One is d rho bar s bar dt plus d rho bar s prime by dt. And here we get 4. We get a rho, oh, this is all rho bar by the way, u bar dx, u bar s bar dx, minus d rho bar u bar s prime dx, minus d rho bar u prime s bar dx, minus d rho bar u bar, oh no, u prime s prime. U prime s prime by dx. And then lots of other things. Okay, so now the one thing that everybody does is effectively we are going to assume, no, we're going to do another average. We're going to average this equation over the grid box again. Yeah?
So it is justifiable to say density variations are small in this case.
Well, so what it's inconsistent with some other assumptions that we're making about our grid books, right? So when we do for the large scale equations, this is an adequate assumption, right? And this is what we're trying to derive here. But later on, we use buoyancy. And buoyancy only works if there are density variations, but the density variations are small. So we're not saying they're zero, we're just saying rho prime is much smaller than rho bar. And so for this large derivation of the large-scale equations, that's a sensible assumption. But for convection, we will have to worry about even those small ones because they give us vertical accelerations. So that's you just need to know what people do. I'm not saying, we're not judging whether it's right or wrong. It's an assumption that is being made. And I think it's a fair assumption for the derivation of the large-scale equations. Okay. Remember the buoyancy, all these large-scale models have no buoyancy because they have no vertical accelerations because they're hydrostatic. So in a non-hydrostatic model, this becomes different, but in a hydrostatic model, we are assuming that there are no density variations in the horizontal. We assume that the atmosphere is in hydrostatic equilibrium in our equation set, right? So we are good, because that's the same thing that we're doing here. So we average again, and then we use some rules from averaging. So one of the rules is that any variable phi prime, if we take the average of that becomes 0. Also, if we take an average of an average, it's just the average itself. And then the other one is that the average over an average multiplied, so phi bar times s prime average is also 0. But phi prime, if you multiply phi prime and s prime and take the average, that's not 0. So we cannot neglect that, because that has to do with the correlations. If this is positive and that positive, and then when this one's negative and that one's negative, the product becomes positive again, so they don't cancel. Right? Whereas these guys cancel, the positives and negatives cancel. Okay? So you have to do that for all this, and I'm just going to write down the end result, because I don't think we want to spend too much time on it, but it will be somewhat surprising end result as well, because we will make there will be other assumptions that you may not know are being made that are actually made. So I'm going to write it as E rho bar S bar dt, and that becomes minus D rho bar U bar S bar dx minus D rho bar V bar S bar y. So this is all easy, minus D rho bar W bar S bar dz. And these are the resolved terms of our equation. And you can convert them to this form by subtracting the continuity equation again at the end, which I haven't done here. Okay, so these are in flux form, the large-scale terms, which in a model our numerical methods will calculate. The dynamical core will do the calculations of this. Then there are two terms which we need to own up that they exist. There's the U prime S prime bar dx minus D rho bar V prime bar S prime bar dy. So these are fluxes of S due to unresolved horizontal motion, right? So unresolved horizontal velocity differences. And what we do with those, so this is unresolved because it has the primes in it, so it's not resolved by our model equations. It's horizontal because it has U and V only in it. So what do we do with those terms in our models? What do you think? What we do with them in our models is this. We neglect them. We say they're small compared to all the other terms. And you can do a scale analysis to convince yourself that this is true for large-scale motion. These are small, but it's an assumption that's made in all models, right? These are negligible. Not zero, but small. Then there's one term that becomes critical, E rho bar W prime S prime dz. This is the unresolved vertical flux. Okay. And then there is plus rho bar Q still left over from way back when. So that's the heating. And now we have to say, okay, in a convecting atmosphere, in our atmosphere where we assume convection can take place, what are the terms that we need to look after? So what is Q? So what's heating in the atmosphere? So one, we know radiation heats the atmosphere, or cools, depending on the sign, right? So we need to include that. And there's a rho, so I'll write it as rho bar Q. Then it becomes rho bar times the radiation. Then we know there's a condensation, that's a heating term, minus rho bar evaporation, and that's it. So evaporation cools, depends on how people define the sign. Sometimes there can be a plus here, and then the E is assumed to be negative. But this is, I write it like this, and then the E is positive. Evaporation cools, condensation heats, radiation, who knows? But it depends on some layers it might cool, some layers it might heat. So there's our equation, and that's what's written there. So really, the left-hand side is the large-scale part, and the right-hand side is, in a convecting atmosphere, will be dominated by convection. So what we are seeing here, and this is where we're going to stop, and we come back to it in the afternoon. Where did I put my thingy? Here. What we're seeing is we have the effect of convection on the large scale goes through these 3 or 4 terms. One is we need to know how much condensation evaporation there is. And we need to describe this vertical flux of, in this case, dry static energy. You can write equations for moisture and other variables in the same way, of course. So convection parameterization then really is about determining what is C, what is E, and what is this vertical flux, right? But we'll first look at what does this look like. The nice thing about this is the left-hand side, if we have an array of radiosones, we can actually measure the left-hand side. And by measuring the left-hand side, we just need to, what's difficult about measuring the left-hand side is we need an average. It means we need, in an area, we need more than one measurement. And usually what people do is they deploy an array of radiosones, like 5 of them in a circle or something like that, to actually estimate what the area average dry static energy changes might be, what the area average wind is, and what the area average vertical gradients are, basically. And from that, we can estimate what the right-hand side is. Okay. To estimate this guy, by the way, W, we need to estimate the divergence and convergence into this area, which is why people use a ring. And then we can use the continuity equation from measuring horizontal winds along that ring or along that circle. We can calculate what the divergence is, and from that we can calculate what the vertical velocity is. Okay? So we'll look at what convection does in this context. These have got names, but maybe I show you that as the last slide. They've become so famous in convection work, they've got their own acronym and their own name. So if you look at heat, then it's the equation we just looked at. So this is called Q1, and it's called the apparent heat source. This basically gives us a measure of the overall effect of convection if you're in a convecting atmosphere on the heat budget. There's an equivalent to that in the moisture equation. Note that there's then no radiation because radiation doesn't affect moisture, and otherwise it looks very similar to this, and that's the apparent moisture sink. And we can derive it by looking at the left-hand side from observations, and that's where we'll start in the afternoon. Okay? No more math. We've done all the math. Whew. Thank God for that. All right. So have a nice lunch, and I'll see you back here at 4.
4 o'clock.